Finally, we are ready to begin traditional calculus. Limit rules and their applications. By the way, we're not going to deal with the precise definition of the limit just yet. Yes, we will, and that's going to be very, very important topic, but not just yet. Maybe several weeks later, or maybe in some other course, but the time did not come yet. At this moment, we're going to concentrate upon limit rules, and we will use those limit rules as the basic building blocks as if those are axioms. And here we go. First, the trivial limit rules. The limit of a constant is the constant itself. Limit as x is approaching c, x is c. They are really trivial. Another way to express this first statement is kind of like this. If k is constantly k, then k is k. Did it make sense? Well, it was so trivial that it sounded so stupid. The second statement is almost equally as stupid. If x approached c, then x approached c. Another tautology. They are trivial limit rules. Next, the addition rule. The limit of sum is sum of the limits. If, this is big if, the limits exist. If f of x approaches L and g of x approaches M as x approaches c, then we have all these. But if those limits L and M do not exist, or any of those two does not exist, then everything breaks apart. Coefficient rule. You can multiply a either before limit or after limit. Again, if the limit exists. Multiplication rule, the same thing. The limit of the product is product of the limit. If the limits exist. If any one of those limits, L or M, does not exist, then everything breaks apart. Same goes to the division rule. The limit of the quotient is quotient of the limits if the limits exist, and also the denominator M should not be 0, of course. Next, inequality rule. Well, here we have some delta notation, but don't pay too much attention to that, or don't be too intimidated here, because we're talking about a certain inequality when f of x is less than or equal to g of x, but that's for pretty close to x, pretty close to x equal to c, excuse me. If f of x exceeds g of x, really far away from c, then who cares, because we're talking about the limit. And also, when x is equal to c, that single point we do not consider. And that's why we have this statement over here. Delta is a sufficient number so that absolute value of x minus c is less than delta. That means x minus c is relatively small, so x is pretty close to c. That's what it means. And the absolute value is strictly greater than 0 means x equals to c. That lone exception does not apply. Anyway, if f of x is less than or equal to g of x, then the limit of f of x is less than or equal to the limit of g of x. One more comment here. If I change this into strict inequality, do I have a strict inequality here too? No, not necessarily. This second inequality has to be less than or equal to. Even if f of x is strictly less than g, it is possible that limits turn out to be the same. Another rule here, it's actually it can be deduced from this inequality rule, to tell the truth, from 1.6, but I decided to put this one too. If f of x and g of x are the same in a certain open interval around c, except perhaps the c itself, then the limit must be the same. Well, around x equals to c, these two functions are the same, so they have to have the same limits. So it's not surprising. But the key part is this: if g of x has a limit and it approached L, then f of x also has a limit and that limit is L. So as for f of x is concerned, the limit exists, number one, and number two, that limit is L. So it's a little bit different from this one where the existence of limits L and M are assumed. In this case, whether f of x converges or not, whether f of x has a limit or not, wasn't clear, but it follows from the property of G. That's the subtle difference between 1.6 and 1.7. Number 8, the sandwich rule. If you have these three functions, g1 of x, g2 of x, and f of x, where f of x is captured in between in a certain open interval around C, here, and g1 of x and g2 of x both converge to the same limit, then f of x is squeezed by those two and must converge into the same limit too. Here's a graphical explanation. The red is the function y equals x squared sine of 1 over x, and blue dotted curves are y equals x squared and y equals a negative x squared respectively, but this x squared times sine of 1 over x is really wildly fluctuating, but it is squeezed by x squared and negative x squared, and consequently as x goes to 0 we have a limit. The limit goes to 0, and here's a good visualization. And finally, the composite rule, and this one we're gonna use only sporadically. Actually, oh, excuse me, I take it back. We will use these, but except for some very special cases, we'll try to avoid this rule because the notion of continuity is very difficult to establish. Anyway, if you have a continuous function, the limit of composite function is some function value of the limit, and that's for a continuous function. And what kind of functions are continuous? Well, basically everything you can think of. Exponential is continuous, logarithm is continuous, all the trig functions are continuous, except for vertical asymptote for some tangents for secants and things like those. Rational functions are all continuous except at vertical asymptotes and things like those. So almost everything you can think of are continuous. And then one application, radicals and exponentials. Well, okay, all right. Because we're not ready to prove all these precisely, our hands are a little bit tied. But we'll do our best using these to establish as much as possible. Okay, here we go. Here are some applications. Limits of polynomials. If you have a polynomial function, limit is just a function value at C. Just like plugging in. And well, here's an application. Here's an example. Yes, okay, here we go. When x is approaching to 2, x squared minus 4x plus 3, well, we can simply plug in and do the computation and everything works right. Okay, how do we prove it? Well, here's a nice version of the proof. Let's see. Any polynomial can be written as this kind of summation notation. An x to the nth power, an minus 1, x to the n minus first power, an minus 2, x to the n minus second power, all the way up to a1x to the first power, and a0 all added up. And then if you use the addition rule, you can addition rule repeatedly for n terms, then the limit of the sum is sum of the limits, so we get the second line. So addition rule repeatedly. Now if you use coefficient rule to each of them, then the AK coefficient can come out. And finally, if you use the multiplication rule 1.4 repeatedly, because this is x to the k power, x times multiplied k times, product of the limit of the product is product of the limit, and apply that repeatedly k times, and we're gonna get that. And finally, this is c, this is the trivial limit rule. So what do you get? C to the k power. And what is this? This is polynomial evaluated at f of c. And that's of course when f of x is this, which is a n of x to the nth power plus a of n minus 1 to the x to the n minus first power plus dot 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 a first power x to the first power plus a 0 power x to the 0 power, and the final term is actually a constant term. In this case, we can abbreviate this expression in the sigma form, and then we end up with this kind of proof. This is relatively naive version because we used repeated application of addition rule right here and a repeated application of multiplication right here. But what do you mean by repeated? We can do it more precisely using the mathematical induction, and here we go. We just established the base case. Well, if you have 0 power, it is nothing more than trivial limit rule, the constant function. And then if you have the first order, then you can prove it like this: addition rule, coefficient rule, and then trivial limit rule. Assume that this one works for n minus first order polynomial, and then use that inductive hypothesis to prove it for nth order polynomial. You can do it like this. First, n minus first terms plus the last one, we can separate these two using the addition rule 1.2. And then this is trivial, this is just a0. And then how about the big limit? Well, we can factor x out, as you can see, and then we can use the multiplication rule 1.4 to get this limit of x out. And that one is trivial rule, it becomes just c. And this one, that's the inductive hypothesis. You can plug in x equal to c, so we end up something like this. After that, just algebraic manipulation, we end up with f of c. And this is a precise proof using mathematical induction. And this one is a little bit more perfect than this naive version where we just use repeated application of something right here and then right there. As a matter of fact, whenever we use repeated application, mathematical induction is actually hidden somewhere. Okay, how about the next one, limits of rational functions? We can just plug in unless the denominator is 0. Okay. Here is an example. You cannot plug in here just yet because denominator becomes 0, but after simplification, Oh yes, you can plug in. And well, that's basically what this theorem is talking about. So it gives us a justification of a limit computation, a typical limit computation that's done by factorization and simplification. How does that work? Well, the before simplification, let's say this is numerator and that's denominator, and we can, let's say they have 0 at x equal to c, then it is possible to factor x minus c to the certain power k out, where the remaining factor is x minus c free, so that's okay. Oh, as a matter of fact, the numerator is not that important. Denominator is important because we do not want 0 in denominator, so factor almost everything out. And then q of c is 0. And then if we simply cancel these out, and what we get, this r of x, and then this p of x over q of x, this r of x and p of x over q of x are the same functions except at x equal to c. You see? Except at x equal to c, just one number, this original and this p of x over q of x are the same functions. And there was that limit rule here. Yes. If we have two functions that are same except for maybe one point in a certain interval, the center point c, yes, in that case, if one converges, then the other converges and share the same limit. Yes, we have that. That's why this r of x can be calculated from p of x over q of x. And then that just becomes, well, repeated rule of the addition rule, multiplication rule for numerator and denominator because they are polynomials, and then finally quotient rule. So we have p of c over q over c, which is actually r of c, the function value for that. And that's how we can calculate the limit of rational functions. Calculation technique is, well, pretty simple. Just factor and cancel out. But justification was rather significant and difficult to prove. Now we have two more important theorems. One is for radical and one is for trig functions. And we're going to spend one whole video for each because they are going to be really, really hard but important.